Drop an atom of sodium into water and it violently explodes. But lock that same sodium atom together with chlorine, and you get perfectly stable geometric crystals of table salt. These outcomes occur because chemical bonds are fluid negotiations of electron density between atomic nuclei, rather than rigid absolute categories. The defining metric of this negotiation is electronegativity. Think of it as a microscopic tug-of-war, dictating exactly how aggressively a specific atom pulls shared electrons towards its own nucleus. This animated diagram shows the lower extreme of the continuum. When the difference in electronegativity between two atoms is less than 0.5, the atoms share electrons equally. This evenly distributed electron cloud creates discrete, nonpolar covalent molecules. As that difference grows to between 0.5 and 1.7, the sharing becomes unequal. The electron cloud shifts towards the stronger atom, generating a polar covalent bond with distinct partial positive and partial negative cols. We can measure this separation of charge as a vector quantity called a dipole moment. This is calculated by multiplying the magnitude of the charge by the physical distance between the charges. Minor shifts along this electronegativity scale dictate macroscopic survival. When chlorine bonds with itself, the zero electronegativity difference creates a nonpolar, highly volatile diatomic chlorine gas, a substance toxic enough to be weaponized in trench warfare. This foundational difference in electronegativity sets the stage for whether elements will combine into inert structural materials or volatile molecular gases. When the electronegativity gap exceeds 1.7, the tug-of-war ends. The sharing ceases entirely, and the more electronegative atom completely captures an electron from the weaker one. This complete transfer forms oppositely charged ions. Rather than pairing off into distinct individual molecules, these ions lock together via electrostatic attraction into massive, repeating crystalline lattices. There is a mechanical exception to this standard sharing model, the coordinate covalent bond. In this scenario, a Lewis base donates both electrons in the pair to an electron-deficient Lewis acid. Once this coordinate covalent bond forms, its physical properties are chemically indistinguishable from a standard covalent bond. The distinction exists purely for accounting purposes. Whether atoms assemble into massive ionic lattices or link via coordinate covalent bonds, the underlying mechanism remains an electrostatic solution, driven by the atomic necessity to achieve noble gas stability. Lewis structures provide a strict two-dimensional accounting system for tracking valence electrons. This diagram maps the formal charge equation: normal valence electrons minus non-bonding electrons minus half the bonding electrons. Applied to nitrogen in an ammonium cation, we subtract 0 non-bonding and 4 bonding electrons from 5 standard valence electrons, yielding a formal charge of +1. Formal charge assumes perfect electron sharing across all bonds. This differs from an oxidation state, which overestimates electronegativity differences by mathematically assigning all shared electrons to the stronger atom. When multiple structural arrangements of a molecule are possible, the most viable physical shape is the one that minimizes both the total number and the overall magnitude of these formal charges. Formal charge acts as a theoretical ledger. It allows us to mathematically predict the most stable arrangement of atoms before we ever examine its physical structure. This accounting system relies on the octet rule, but treating it as an absolute law is a mistake. Elements like hydrogen, beryllium, and boron are stable with incomplete octets. Elements in period 3 and beyond present an even larger trap. They can hold significantly more than 8 valence electrons by utilizing empty d orbitals to expand their octet. This diagram demonstrates resonance. When a molecule's electrons are delocalized, we can draw multiple valid structures, like these two forms of a sulfate ion. The molecule doesn't physically flip back and forth. It exists as a permanent, blended hybrid of all valid resonance structures. Breaking the rigid octet and utilizing resonance allows molecules to distribute charge more broadly, ultimately achieving lower energy states than standard two-dimensional accounting would suggest. To translate these flat layouts into actual shapes, we use valence shell electron pair repulsion theory. Because electrons carry the same negative charge, pairs of electrons repel one another in three-dimensional space, orienting themselves to maximize their physical distance. This repulsion creates two distinct geometric profiles. Electronic geometry describes the overall spatial arrangement of every single electron domain around a central atom, counting both bonds and non-bonding lone pairs. This diagram shows the two-dimensional structures of methane, ammonia, and water. Molecular geometry maps only the arrangement of bonded atoms. Methane has 4 bonds and 0 lone pairs, creating a pure tetrahedral shape with highly symmetrical 109.5-degree bond angles. Non-bonding lone pairs sit closer to the atomic nucleus, exerting a significantly stronger repulsive force. In ammonia and water, these lone pairs crush the bonds downward, forcing narrower trigonal pyramidal and tight bent geometries. Knowing a molecule's true three-dimensional spatial geometry, rather than relying on a flat schematic, is the only rigorous way to predict how it will physically interact with other molecules. This three-dimensional geometry directly determines molecular polarity. A molecule can contain individually polar bonds, but that does not guarantee the overall molecule will be polar. Overall molecular polarity is determined entirely by the physical vector addition of all internal bond dipoles in three-dimensional space. In carbon tetrachloride, 4 polar bond vectors pull equally in opposing directions, symmetrically canceling into a non-polar molecule. Contrast this with water. Its bent geometry prevents cancellation. The vectors sum together, generating a powerful central net dipole. Structural symmetry can neutralize intense internal polarity, defining the molecule's eventual macroscopic behavior. Once we understand the individual molecule, we can map how billions of them interact in bulk. This requires intermolecular forces, the forces that dictate macroscopic properties like boiling and melting points. Intermolecular forces are strictly electrostatic attractions between discrete molecules. Because they act across greater distances, they are inherently weaker than the covalent or ionic bonds holding the individual atoms together. At the lowest end of the hierarchy are London dispersion forces. These are transient attractions caused by the rapid, unpredictable shifting of electron clouds, which creates brief, momentarily induced dipoles in nearby molecules. Because dispersion forces scale up with a molecule's size and surface area, their collective strength can be massive. This is why even entirely nonpolar noble gases can be forced to condense into liquids. Moving up the hierarchy, we find dipole-dipole interactions. These occur exclusively in polar molecules, which physically align themselves so their permanent opposing partial charges attract. As an individual molecule's dipole transitions from a temporary shift to a permanent feature, the macroscopic electrostatic grip of the bulk substance scales up right alongside it. The pinnacle of these interactions is hydrogen bonding. Despite the name, this is an extreme, unusually strong form of a dipole-dipole interaction, not an actual covalent bond. It requires a strict prerequisite. Hydrogen must be covalently bonded to a highly electronegative fluorine, oxygen, or nitrogen atom. This pull leaves the hydrogen nucleus stripped of electron density, exposing the naked proton. This exposed proton interacts powerfully with the partial negative charges on nearby molecules, allowing for tight intermolecular packing. This mechanism explains why water requires a massive amount of thermal energy to boil compared to molecules of similar mass. The precision and strength of hydrogen bonding extends well beyond boiling points. These interactions are responsible for stabilizing the most critical macroscopic architectures in biochemistry, including the rungs of the double helix DNA structure. We can trace this entire predictive methodology backward. The bulk material properties of a substance rely on its intermolecular forces. Those forces rely on the specific 3D VSEPR geometries of the molecules, which rely on the strict 2D accounting of formal charge. This predictive methodology forms a continuous, scalable logic sequence, starting from the electronegativity of a single atom and ending with the physical reality of the entire universe.